So what exactly is an RV321? An RV321 is a modern operating system and it is used to reduce the hardware complexity. In general, there are actually 47 instructions over here, but in this project, we are only going to implement 41 of those instructions. The details of which instructions are to be executed are in table 3 of the leaflet that has been provided to us. So let me just go through really quickly what's happening over here. So you would see initially there's a program counter, which is labeled as PC. Now, what does a program counter do? A program counter contains the address of the next instruction to be executed. From the program counter, it goes to the instruction memory. So what does the instruction memory do? Instruction memory, it contains an output and a function field, which is in an R format. R format has the first 6 bits dedicated to the output, followed by an RS, RT, and RD. And then you have the function code. There's a register file over here, which contains the RS1, RS2, and RD. So RS1 is the source register 1, RS2 is the source register 2, RD is the destination register. Okay. So these are register files. It has 2 independent registers, read, and 1 register write in 1 clock cycle. Followed by that, we have a control unit. You could see over here. Now, the control unit, the type of instruction then determines so depending on the instruction that you're getting from here, the type of instruction then determines which control signal are to be generated and what function the arithmetic logic unit needs to be executed. The details of the encoding of those instructions are in the table 4, the thing that has been provided to us. So the control unit can either perform an arithmetic operation, like an XOR, AND, or AND, or it can do a comparison, or it can also compute a memory address, which is in the load or a store format. The ALU result needs to be stored in a register as well. And the data memory, which you see over here, serves for storing and keeping the data required for the proper operation of the program. So this is basically the basic components that you will find in RB321. What we try to do over here, we try to execute, we are trying to make individual components of this one, and then we are going to compile them together and try to execute how an RB321 is going to happen. So in the next step, I'm going to show you how that's done. So now so in milestone 2, our focus was basically create individual components. You could see over here the individual components include creating a program counter, creating a control unit, creating a register file, creating an ALU unit, as well as an instruction memory. Uh, yeah. So this were the different files that we had to create, and each one had their individual test benches. So this is basically a time scale simulation from here. As you could see over here, just scan it. So the program count is supposed to increment by 4. Okay, so these are the different test cases written over here. If you could see over here, these are the different test cases that we tried to check over here. And this are for the control unit. This included all the test cases that we were trying to do over here for register file as well as for ALU and instruction memories. For instruction memories, all this are basically from table 3 or table 4, I guess. And we tried to make sure that it actually works over here. And yes, so that was basically here. Next step, I will basically show you a demonstration on how we try to connect it to an FPGA board and try to see whether the program counter works or not. So we'll start with the program counter right now. As you could see over here, what we tried to do over here with the program counter, I set V17. V17 is the reset pin over here. And the other pins all the way from PC0 out 0 all the way we have assigned the pins. You would see that PC1 is E19. Okay, so let me just bring you over here. Now you could see over here that it was all working. Now when I'm bringing it over here, you could see again the reset pin over here is V17. So let me just bring you over here. And you can see on focus over here, this is your V17. Okay, so when I'm pressing it over here, you would see only one of the pin, which is in this case T. Let me see properly. T11 is the one, so it's 0100. Okay, so that's how the reset pin is set. So it's 0100. Okay, again, when I'm using the reset pin. Okay, so now what I'm going to do is I'm going to show you the Vivado file, which was basically used to combine all the different components that I just talked about. You could see over here, this is the source files. So this was the ALU, as we discussed earlier, the control unit, the data memory, the instruction memory, the program counter, the register file, everything is over here. And this one is combining all of this over here. We used port map initiation. That's the technique that we try to combine all the files over here. And you could see over here when we tried to run the simulation. So this is what we got over here. You can see a time scale representation of like the clock cycles over here and the different components over here. So let me just pull up my new file over here so that you could see it over here. Just give me 1 second. Now, where did I have? So it was this one. Okay. So let me just walk you through like what's happening over here. Now, over here, this is the overall representation of what's going on over here. I've written it down in the milestone too. Let me explain one of those clock cycles, and you will be able to see over here. So this one, the opcode was for SB. So you would see at 60 nanosecond, the opcode is this. This opcode was called the store byte. The function of the store byte is to store the lower 8 bits of your RS1 from one register to the other. So at 60 nanoseconds, you would see over here, the lower 8 bits of RS1 is stored in RS2. Let me zoom in a little bit. Yeah, I think like now you guys could see the time scale. So this was the opcode 010011. You would be able to find it in your data table. From there, you would find that it was SB, which was the store byte. The store byte function was basically to store the lower 8 bits of RS from one register to the next. Another overview that is actually working is the opcode for LHU, which was this. Like you can find it all in the data table. So at 20 nanoseconds, you would have seen that this opcode is for LHU, which is load half word unsigned. The function of LHU is to load a 16-bit unsigned value from the memory at the address specified by the sum of the contents of register RS1 and signed extended immediate value. 0 extend the 16-bit values to 32 bits and store it in register RD. Hence, at 20 nanoseconds, the value of the RD has been updated. So initially over here it was, but when you see this clock cycle, it has been updated. You would find that the updating is taking place because of the opcode is basically LHU, which is the load half word unsigned. Okay. So Now what we are trying to do is we're trying to do the high level encryption using RC5. So just as you could see over here, this is the source code over here. And you could see over here, there's no error. Okay, so in theory, it should have been working. However, when we try to use the test bench over here, you would see that there are multiple errors. We tried to use LLM, like ChatGPT, to figure out what could be the sources of error. So you can see over here, we tried it multiple times. We provided like the source code over here. We tried to figure out like every time they were trying to give us something that we could do. Bottom line, that one of the error that they were constantly suggesting, as I've mentioned in my report, is that that uh, the RC5 data out signal is might not have been connected. So that is what they're trying to say over here, which is also kind of pointed out by the TA as well, that maybe it's not connected. The data out signal is not directly driven by the RB5 unit, and there could be one of the reasons why it's not working. We tried a lot of times, we are not getting it, but we did get, as you could see over here, uh, so over here, like if we try to run this behavioral simulation, getting something, but it's working as you can see, a lot of it everything, which means that test bench is not working, but the source code, the top model is supposed to work. But since the test bench is not working, that's why it's getting this error. But we would keep on trying to figure out what it is. But yeah, well, uh, yeah.